In this review, we're going to cover matrices, which we'll find a couple of good uses for in physical chemistry. So the main uses we'll have for these will be in the latter half of the semester, and we'll use them to discuss the multiple dimensions when we're talking about symmetry and group theory, and we'll also use them to construct atomic orbitals out of individual orbitals occupied by electrons in multi-electron atoms. So I want to start out by just reviewing what a matrix is. So matrix has multiple dimensions. There's rows and columns, and they're listed rows first and columns second. So here, if we have a 1 by 2 matrix, that means there's one row, one thing going from top to bottom, and two columns going from left to right. And you can see an example of that here. And another example here would be a 3 by 1 matrix, which would have 3 rows and only one column. Now, multiplying matrices can be a little complicated if you haven't done it in a while. And they have to have dimensions that match, and it's not necessarily the same dimension. So, for example, if we want to multiply two matrices, A and B, multiply them together, and our A matrix has an n by m dimensions, then our B matrix has to start with the dimension m, and then the second dimension doesn't matter, so it can be m by p, and then the resulting matrix will have the dimensions of n by p. So, for example, if our A matrix is 2 by 2, such that it's 1, 4, 3, -2, our B matrix has to have 2 rows. If it does not have 2 rows, we can't do A times B. So our B matrix, let's make it 2 by 3, and we'll make it 0, 2, -1, 4, -3, 1. And we can multiply these two together. Now, note that if we can multiply here AB, which we can do, let's check real quick. So we have 2 by 2 and 2 by 3. Perfect. We can multiply them by each other, and the resulting matrix will be 2 by 3. We cannot necessarily do B times A. So if we switch it the other way around, we do 2 by 3 and 2 by 2. We'll note that these two dimensions do not lie up. So while we can take an AB matrix, we cannot take a BA matrix. We can't multiply them in the other direction. So to actually multiply these two matrices, I'll go ahead and rewrite them here. What we do is we take one row and then multiply it by an entire column of the matrix. So for example, if we want to find the first entry of our new matrix, we need to take the top row and multiply this by the first column. And so what that looks like is 1 times 0, so we multiply the first two entries, and then we add the product of the second two entries. So 1 times 0 plus 4 times 2, and that equals 8, of course, and so 8 is the first entry in our matrix. And now we'll pick another one. And so if we wanted to find another entry, so let's say we took the second row, and we multiply that by the second column, we do the same thing. We do 3 times -1, and then we would add to that -2 times 4, and so that is, of course, -11. And since we're doing the second row and the second column, that's going to put us in the second row and the second column of our matrix, so that's going to put us in the slot right here. I'll fill in the rest of the solution for you, and you can check it on your own to make sure you're following. But the total solution of our AB matrix here is as shown. So 8, 15, 1, and then -4, -11, -11. All right, so that's how we multiply matrices, and we'll do some of that over the course of the semester. And what we'll also do is we'll take determinants of matrices. So to start, we'll look at a 2 by 2 matrix. So we'll use our example of A up here and also just an arbitrary one. So to take the determinant, we use these straight lines rather than the typical matrix brackets to indicate that we're taking a determinant. So if we're taking a determinant of our matrix ABCD, the determinant is this product here, so AD, minus this product here, BC. And that is the determinant of a 2 by 2 matrix. So for example, if we want to take the determinant of A, we'll take the determinant of 1, 4, 3, -2. That's going to give us, so A times D is -2, and minus B times C is 12. So the total answer is -14 is the determinant of our matrix A. We'll often run into taking the determinants of 3 by 3 matrices. So the book will go through a tedious way of doing this, and you can use this if you wanted to say take the determinant of a 4x4 or 5x5 matrix. But we won't be doing anything like that in class, so I'll leave that to the book if you're interested. And I'll just show you a shortcut here of taking determinants of 3x3 matrices. So if we have a matrix that's A, B, C, D, E, F, G, H, I, a 3x3 matrix, we want to take the determinant. What we're going to need to do is take a bunch of products and then add and subtract them in a similar fashion to what we did up here. And so the way to do that is to extend the matrix. You can either do this, physically on the paper like I will, or just do it in your head. But I'm going to go ahead and write the entries preceding here. So cycle, so we have D, E, F, and I'm going to write D again, so cycling the entries, and I'll cycle them in the reverse direction as well. And then the products we're taking are going to be very similar to what we saw above. So instead of just taking the one cross product, now there are three we're going to take. So we're going to take AEI, BFG, and CDH. And these are going to be our positive entries here. So the determinant of this 3x3 matrix is going to be AEI plus BFG plus CDH. And then in the other direction, we have three more products here, and those are going to be subtracted. So then we're going to subtract CEG minus BDI minus AFH. And you can see that this is kind of a larger dimensional process of the simple 2x2 determinant we did before. But this is a quick and easy way to calculate 3x3 determinants. And so we'll do both the matrix multiplication and the determinant determination, I suppose, over the course of the semester.